So this video is going to be talking about potential energy and the conservation of total mechanical energy. So we're not looking at a broad-based conservation of energy concept like the total amount of energy in the universe is constant and it just changes from form to form. That's a tale for another day. But really what we're trying to get to is our understandings about potential energy. And we're going to get to this by talking about gravitational potential energy. So here I have a surface. Let's say I have an object on the surface. There it is. We would say that this object on that surface has zero gravitational potential energy. Why? Well, we said that potential energy was the capacity of an object to affect the environment due to its location and the existence of a specific type of force, in this case, the gravity force. We haven't really answered the question very well, like why the gravity force and not other types of forces. That's the point of this video. It's like, what's special about the gravity force that means it has an associated potential energy? And then how do we bring this all together? But we know that this thing doesn't have the capacity to affect the environment. No one will be worried about it. It doesn't have the ability to hurt you just sitting there. But if I were to bring it up to this level here, some height above the ground, some displacement upwards, I think we would agree that at this new height, that this object, this mass, now has the capacity to affect the environment because of its location, specifically its location above the ground. If we were to drop that, that would be, it would hurt if it hit you. So we know that it has the potential to affect the environment, i.e. it has potential energy, the capacity to affect the environment because of its location. Okay. A little long-winded here, but the words matter, so I'm probably going to say them over and over again. So we know in order to go from here to here, that's not going to happen naturally. Some force would have to do work in order to get that object up there. So let's say I apply a force like this, and it does work to get me up there, and I know that the gravitational force is acting simultaneously. And so if I lift the object from here to here, I am doing work, and gravity is doing work. So let's talk about the work done by the applied force here. I think we can see pretty easily that the work done by the applied force would be positive, right? Because the applied force and the displacement are in the exact same direction. But the work done by gravity here is going to be negative because the force of gravity is down and the displacement is up. We would have the angle here is 0 degrees. The angle here would be 180 degrees. Well, why? Let's go back to our original idea that work is positive if that force is trying to speed an object up. So if the applied force is acting in the same direction as the displacement, that's trying to speed it up. Gravity is trying to slow it down. As I move upwards, those all check out, okay? So let's just kind of keep that in mind. Now, in this case, I could say if the object started and stopped at rest, we could say that the net work here would be equal to the kinetic energy, so it's the work done by the applied force plus the work done by gravity would be equal to, in this case, KE final minus KE initial, KE initial. Both of those would zero out, and that the applied force would just equal the negative of the work of gravity. That sort of like gels with what we're seeing down here. One's positive, one's negative. There we go. But they don't have to. Like if I do more work than gravity does, when I get here, that object would just have a velocity upwards. Right? And if I don't do enough work, well, that thing's never going to get off the ground. So we're not even going to look at that scenario. But that's the little neat thing there. Now, here's where it starts to get interesting. Rather than me bringing the object to here, now I'm going to bring the object here. So this was position 1, this is position 2. Okay? Notice now my applied force would have to go here at this angle, so this is gone now, right? And my displacement could be like this. Notice here that the applied force is going to have a larger displacement here if I'm moving over there. So the work done by the applied force is going to be different than just lifting it straight up. But if I look at the work done by gravity, okay, in this new instance, right? Here's my displacement, here's the force of gravity. The angle is no longer 180, it's still some sort of obtuse angle. But at the end of the day, the interesting thing here is that all that's going to matter is not this displacement, but the vertical component of that displacement. Because if I look here at this little diagram, that this displacement delta s could be resolved into delta y and delta x, and the delta x portion of this displacement would have cosine of 90 when I would go to do the work. And so the only work that matters here is the work done along this vertical, right? So all that matters here is still that same displacement. So interestingly enough, the work done by gravity is the same going here or it's going there, right? And then if we start getting even more interesting, but by the way, the work done by the applied force is different along going from here to here rather than from here to here. But if I then again look at an even weirder way to get from my original position to 1, once again, the applied force is going to have to change its direction all along, and then we'd have to like deal with all the little bits of displacement, and the work done in that case by the applied force is going to be all sorts of wacky there as well. But the work done by gravity, again, it's only going to care about that vertical part. Every time, every component of displacement that happens side to side because of the cosine in our work equation is just going to zero out. So this brings us to a really interesting thing. And by the way, the proof of this is so much more complicated in a formal sense. The idea is there that no matter what, the work done by gravity to go from height 1, which was the ground, to height 2, which was that space above, was the same irrespective of the path taken to get from height 1 to height 2. But by contrast, the applied force would do different works on different paths between height 1 and height 2. Therefore, for gravity, since it's the same work that gets done going from height 1 to height 2, there's something special about each height. It's like I could write an equation that says something about this position and this position, that no matter what, going from here to here, it's the same amount of work done. So we can talk about like the position itself is important because irrespective of how I get from here to here, it's the same amount of work done. So I can write an equation that talks about that position. Now for the applied force, I can't talk about an equation for that position because I get there in different paths, right? Sorry, if I get there in different paths, it takes different amount of works. So there's nothing special about that location, okay? So a long way around to say, there exist two types of forces in this universe, okay? And we're gonna give titles to them, and here we go. One is a force where the work done between 2 points in space does not depend on the path from 1 to 2. We call these forces path independent, right? Or not the forces path independent, but that's the phrase that's important, right? Whereas a force where the length of the path affects the amount of work done. And these are going to be path dependent. We're going to end up calling these forces where the work done is path independent conservative forces, and these forces are going to be non-conservative forces. And so therefore, or then our examples of these, well, gravity is clearly conservative because the path doesn't matter, and our example here was an applied force. So thinking about this as well, if I start talking about in here, the frictional force there, right? The length of the path matters because as the pen is moving across that path, right? Every time I move over any little bit of ground, you can literally hear sound, right? You can hear, and we know that heat is dissipated, right? That is energy that's leaving the system in some other form, right? The length of that path matters. The more I rub my hands together, the more energy it's leaving the system. So I think we can make an argument that friction is also non-conservative. And if friction is non-conservative, so is air resistance. Okay? If the applied force is non-conservative, so are normal forces. Okay. So if gravity is a conservative force, well, what are some other forces? Well, this might be a bit of a stretch, but I said that as a pun because the elastic force is also a conservative force. The work doesn't depend upon how I get there. It only cares about the beginning and end state. How much did I stretch the spring? How much did I compress the spring? Once again, the proof that this path independence is actually a very high level calculus idea. So we're gonna kind of like go with it. We're also gonna say the electric force, the magnetic force, and also the nuclear force. I think the important thing I can say is all of these forces, we already know the equation for the gravity force. Fg is equal to big G m1 m2 over r squared. We know the elastic force, the spring force magnitudes, by the way, K delta x, or Kx really, right, for the position from the equilibrium. Notice that this force is position dependent. This force is position dependent. These are all position dependent forces. None of these are position dependent force. Doesn't matter where you are. Doesn't affect the applied force. Friction doesn't matter where you are. Well, it matters the surfaces that are in contact, but the location in space doesn't affect the frictional force. So these conservative forces are all location dependent, which means it should make sense that the work done, that's a connection that connects to the fact that the work done doesn't depend on the path between the points, but only what the points themselves are. You'll also note that this list is very familiar because we also said that there were potential energies associated with each of these. Okay, so there we go. And so we'll start with the potential energy due to gravity, and we'll kind of like build it up from there over the course of the course. So that's what we've got. So what does that mean for us? Well, very simply, another way to think about it. Here we go. I have this object. Well, I'll even just like, here's my calculator. I lift the calculator, right? I gave it potential energy. Initially, how much potential energy does this object have? Nothing, sitting on the table, right? No kinetic energy. Lift it up. This now has gravitational potential energy, has no kinetic energy, right? So notice then in this lifting up, the total energy of this system changed, right? It went from 0 to something. And then let it drop. And then as it falls, just before it hits the ground, it has kinetic energy, but functionally no potential energy. To look at that in a drawing, here at position A, the total energy of the object is equal to, well, the total energy of an object, the mechanical energy is the kinetic energy at that point, plus the potential energy due to something, in this case, gravity at that point. We know that both of these are 0 at that location. I then raise it. This is position B. So this is moments in time, by the way. So at this location, at position B, the kinetic energy at B, we said it's at rest, but the potential energy at B exists. So now the total energy of the system is larger than 0. And then position C is just before it hits the ground as it goes. So we'd say the energy at C, the kinetic energy is not equal to 0 because it's moving at that point, plus potential energy due to gravity at C is virtually nothing because it's basically on the ground. We'll get an equation for this in a little second to kind of help us out with that, but there we go. So the important thing is here to go from A to B, the applied force did work and gravity did work. Go from B to C, only gravity did work. And so we're going to see another aspect of conservative versus non-conservative forces here as well. So going from A to B, I did work and gravity did work. Going from B to C, just gravity did work. Notice when it went from A to B, the total energy of the system increased, right? So there was a positive change. That was terrible. There was a positive change in the total energy of the system. Very clearly, it had zero total energy here, and now it has some, so that's an increase. But from here to here, what seems to be happening here is that potential energy is what I have here, and kinetic energy is what I have here. So what we're going to find out is that from here to here, the total energy of the system remain constant. Okay, so what's different between the two situations? Well, it's the existence of the applied force here, right? Because the work done by gravity is the same, is there in both places. So another aspect of these types of forces is for conservative forces, when they do work, the total system energy does not change. Instead, what the work done by these conservative forces do is it turns either potential energy into kinetic energy or kinetic energy into potential energy. Okay, so here, as I'm trying to lift this object, what gravity is doing is taking that kinetic energy I should be gaining going up to A and turning it into potential energy. And then when I let it go, the potential energy here is being turned into kinetic energy. But non-conservative forces, when they do work, notice not when they act, when they do work, the energy, the total energy of the system changes in amount. Okay, so there we have it. When they do work, the total energy of the system changes in amount. Okay, so written another way, when the work of non-conservative forces is non-zero, the total energy of the system changes. So this becomes a new premise for us. Okay, but if the work done by non-conservative forces is equal to zero, therefore the total change in energy is zero. And therefore we can write a law. And this is the law of conservation of total mechanical energy. And what that says is, in the absence of non-conservative forces doing work, the total energy of the system remains constant. That's a mouthful, so I can write it symbolically. We can say that the energy of the system at one point is equal to the energy of the system at the other point, if and only if the work done by non-conservative forces as you go from 1 to 2 is equal to 0. Okay, I do want to reemphasize the fact that this is not saying that non-conservative forces don't act, it's just that they don't do work. Okay, so there we go. Non-conservative forces do work, total energy changes. No non-conservative forces, total energy remains constant. So I'm going to leave it at that, so we now know what conservative versus non-conservative forces are, right? Conservative forces, they are forces that are all position dependent. When they do work, the work is not path dependent, and when they do work, they convert potential to kinetic energy. Non-conservative forces, the amount of work depends upon the path length, right? When they do work, they change the total amount of energy in the system. Their forces are not position dependent. This video is running long, so we're going to stop here, and then we'll look at this in problem solving in the next video.